So this is the second installment on tutorials on optimization methods. I see that Steve Wright did a very good job. He did all the heavy lifting. And therefore, what I was planning to do this afternoon, given that it's so late, is to cover just a few topics and cover them pretty slowly, pretty down in depth. So in particular, I'm going to be looking at deep nets. And for instance, I know that Hessian free methods are considered to be an alternative. I'm going to go into some depth into that. There's a big discussion about stochastic versus batch methods. I'll talk about this. And I'm going to also talk to you a little bit about the type of complexity analysis that I think we need to do. I'm not going to get into the mathematics. I'm going to get into trying to explain what is the idea? What is it that one needs to do to evaluate such methods? Okay, I'm going to start by talking about some of the characteristics of optimization problems that arise in deep learning. I'll also be looking at convex logistic regression. And I'll talk about inverse covariance estimation. I'm not sure how much interest there is in that problem, but it's going to be a very good way to test the power of some of the optimization ideas that we have there by taking them into a totally different domain, exploring them there. All right, so from the optimization point of view, there are really many tools at our disposal for solving machine learning problems, for training and supervised training. There are first and second order methods. There are batch and stochastic algorithms. One can try to use regularization and promote sparsity. There are primal and dual approaches. And we have parallel and sequential computing environments. So that's a lot, and one can easily get lost. What is the right tool for the right problem? Now, in spite of the fact that we have so many tools, the state of affairs concerning deep learning is very confusing to me. Maybe it's not confusing to others, and I'm talking now from the point of view of optimization. It's very confusing to me because too many challenges are being confronted at once. There is the issue of local versus local minima, training, pre-training, initializations, stochastic versus batch, heuristics. And I hope that in this conference will help me also to figure out a little bit more how to attack things. So in my opinion, and in particular for deep learning, we need to isolate the questions that relate to optimization and study them in isolation. So we have so many variables in deep learning that if we want to make progress from the point of view of creating new optimization algorithms, we're going to have to isolate questions. For instance, the question about local minima. And are we looking at generalization errors? Or looking at training errors? And what can we say about the global optimization properties of stochastic methods, for example? One of the most important questions talking to people like Jan and Andrew Ng and so on is stochastic methods versus deterministic methods. What can we say about them? And to me, I'm not unsure. So some groups say, I can train neural nets very well in a batch setting. Others say, I have to use a stochastic method. After some clarity is obtained, we need to develop appropriate algorithms for these problems. And we need to develop what I would call not iteration complexity that Steve studied in some detail here. He explained it in detail here. But what I call work complexity bounds. And Botu is one of the people who's done some of the most interesting work along these lines. Let me tell you what I mean by work complexity. Suppose that someone tells you that there are two optimization algorithms, two competing optimization algorithms, and they tell you the rate at which convergence is attained. So you can have a statement such as the total number of iterations to obtain an epsilon accurate solution is 1 over epsilon. Okay, the two methods may have the same complexity, iteration complexity bound. But suppose that one method is a lot more expensive than the other one. How is that useful? Now, what work complexity is about is to estimate what is the total number of flops that will be required in order to obtain an epsilon optimization solution. And I'm going to give you some results here. That kind of complexity clearly is more difficult because it requires first the rate of conversions result, and then it requires an understanding of how much work there is. And some algorithms have a variable amount of work, so that can be difficult. But this is a frontier that I think is a very interesting thing to look at as we develop optimization methods. So as I mentioned at the very beginning, I will discuss only a very few optimization methods because Steve Wright presented a big panorama of them. And I will sit for a while and give you some insights about some of these methods. Stochastic versus batch. What I have to say about this is I will talk about methods that are neither purely stochastic nor purely mini-batch. But I'm talking about methods that keep changing the sample size with the iteration. Can one construct algorithms in a rigorous manner that's not heuristic? And can one get good work complexity result for that? So that's a topic I will look in detail. And the other thing is, because I belong to the optimization community, we look for general purpose techniques. That means algorithms that are not just appropriate for one application, but probably useful for dozens and dozens of applications. I'm going to look at the use of second-order information that is not very common in machine learning. And when I talk about general purpose methods, we're going to be looking at things like scale invariance. So Steve Wright talked a little about this. We don't want a method that works very well on a problem. Then there is a rescaling of that problem, and the method suddenly works very poorly because parameters were adjusted to that scale. We want scale invariance. And one of the things I'm going to argue during this presentation is we can never obtain scale invariance. For large problems, scale invariance is too expensive. But what we're going to do is try to get as close as possible to scale invariance. There is a continuum. There are algorithms that are totally dependent on the scale, and there are algorithms that are less dependent on the scale. I will explain that. And heuristics are very important in practice. One knows that it can make a difference, but we will stay away from those because we will try to look at general purpose techniques. So finally, before I dive into the material, I have to explain a little bit about my background. Most of my practical experience in optimization methods for machine learning has been for speech recognition. For a couple of years, I worked with a group at Google, and we were doing, for that particular application, we were doing logistic regression. And we wrote couple of papers that I like very much. So although my practical hands-on experience was limited to that, I am aware of a lot of experiments that are being done in many places using optimization methods for various machine learning applications. And I learned them because people contact me about advice, or I'm using this code, what do you think about that? And then I dive and look into such issues. Recently, I developed this Hessian free method that was developed at the same time and in parallel in the machine deep learning community. And I get a lot of email from this Hessian free method that we developed. And in the end, what I would like to do is I would like to design optimization methods that are particularly effective for machine learning applications. And the area that I find the most challenging is deep learning, because at this point, I don't know exactly what is the way to go. Okay, so let's start now with the talk. How about if I give you a couple of intriguing statements? There's a very nice paper by Bottou and Bousquet that talks about, I think the title is The Trade-offs of Large-Scale Machine Learning. And towards the end of the paper, there's a statement that says something along the following lines. The best optimization algorithms are not the best learning algorithms. I will dissect that sentence later on, and then I'll challenge it. So I'll try to find some other space. Because this statement is not very encouraging, right? We seem to be contradicting ourselves. There's another sentence there. Stochastic methods are the best in spite of being the worst optimization methods. So we need to make such statements a little bit clearer for us. Now, when Bottou and Bousquet made such a statement, there's a lot of foundations for making such a statement. And I chopped the sentence. They said that when taking into account estimation and optimization errors, then what you would consider to be the best optimization algorithms may not be the most appropriate. And we'll look into that. But of course, what we have in machine learning essentially is we're trying to use prediction functions that are not perfect. And we're not using the true expectation, we use empirical expectations. If you have such errors, you don't need to do optimization accurately because you're exactly solving a problem that's the wrong problem. So if you want to balance these three errors, then you may find out the different techniques are the most appropriate ones. But in any case, those are intriguing statements just to get us going. Okay, I will not say a lot about problem characteristics, but neural nets, if tackled in a naive way, are extremely nonlinear. And a lot of what I've learned about neural nets is from discussions with Clement Farabet, where we were able to make a few controlled experiments that gave me a little bit of a feeling of how things work. Now, if someone would ask you, if some general person in the street, in the bus, in the subway, asked you, what is a very nonlinear problem? Do we know what's the meaning of a very nonlinear problem? In fact, there was a young PhD student who was telling me, you know, I'm working on neural nets, and this problem is far more nonlinear than probably anything you've ever seen. And so I asked the student, what do you mean by the most nonlinear? Do you mean this? Or do you mean that? And in fact, there was no answer because such a concept does not exist, the most nonlinear problem. And in fact, the math department is just across the street. We can find functions that are not analytic and have an infinite number of minimizers that are not isolated. We can find extremely bizarre problems, right? This here is a question of ill conditioning. There's a lot of curvature and there's ill conditioning. This is the question of many local minima. Very hard to solve this problem here in high dimensions. Not so hard to solve with this problem here if you try to incorporate second order information. Very hard to solve a problem like that if you don't incorporate second order information. But so how does it look? And well, it's also going to depend on how do you define your neural net. I took this objective function from the article by Andrew Ng and Lee and so on, and that was presented here last week. And so you're familiar with that. Here we have the activation functions and some nonlinear functions. So we know something about the classes of functions that we want to minimize in practice. And they may include a regularization term here. And this is another one of the themes I will try to cover in detail during the next few lectures. Okay, how about if I consider the following general formulation? I'm going to say that the optimization problems we want to tackle have this form. They're a sum of loss functions plus a regularization term. Now, it would be easy for me to write a general regularizer. How about if we just write the one norm? And later I can tell you how things generalize. Let's just assume that it's the one norm. There have been some excellent talks here about promoting sparsity and the use of the L1 norm. So I think all of this material is pretty clear. What is the loss function here? Well, we could have convex functions or we could have non-convex functions. But let us start by ignoring the fact that there is regularization. Let's suppose that we have just a simple loss function. And let's simplify then the notation and say that the optimization problem is going to be written as minimize some function, unconstrained function of some variable x. So although the parameters here were w, now the objective function is going to be a function of x. Let's call it x to have standard notation. And the first big method I want to talk about is the Newton CG method. And many people in the machine learning community know it as the Hessian free method. To tackle the unconstrained problem, minimize f of x, regardless of whether it's convex or non-convex, you can simply pretend to apply Newton's method to the problem. So here's the Newton iteration that has the Hessian matrix, the gradient, and the search direction that comes out of here is the Newton direction, the classical Newton direction for optimization. Then you take that direction and you step a certain length alpha along that direction, and you repeat the process. This is the perfect Newton method, the classical Newton method, and it's totally impractical for very large-scale applications because the Hessian matrix is very expensive to compute, very difficult to solve, and so on. But for the time being, let's suppose that we could do this. We could do the perfect classical Newton method. Okay, so in order to compute a search direction, we need to solve a linear system of equations of size n. N is the number of variables. Now, for neural nets, we would have a dense matrix here. For logistic regression, for most problems, we would have a dense n by n matrix. In many applications, the number of parameters could be in the thousands, hundreds of thousands. This is an incredibly expensive system to solve. Nevertheless, let's stay with that. Suppose we do Newton's method. Now, if we cannot really solve that problem, we're going to apply an iterative method. Iterative methods for solving linear systems are really effective tools for exploiting approximate solutions and for being able to solving very large problems. And the perfect method for solving linear systems of equations that are symmetric and positive definite is the conjugate gradient method. One can argue that there's no better iterative method. There are methods like Gauss-Seidel, projected Jacobi, GM-res, and so on. There are many methods for solving linear systems of equations, but if you have a symmetric and positive definite system, one can argue that the conjugate gradient method is optimal. And I will describe some of the properties and how they interact with what we want the optimization algorithm to do. Now, we're going to apply the conjugate gradient method to obtain an approximate solution to the Newton equations. Why approximate? Because an exact solution is going to cost too much. An approximate solution is obtained by applying only a few iterations of the conjugate gradient method. But it turns out that while applying a few iterations, the method has such interesting properties that we're going to be producing productive steps. And the more CG iterations we perform, the more productive the direction is from the point of view of optimization. I will explain that. Finally, another very interesting property of iterative methods, and that's not just of the conjugate gradient method, is that if you look at this system of equations and you solve it with an iterative method, you don't have to form the Hessian matrix. It is going to be enough to be able to compute the products of Hessians times vectors. And I will also explain, I'll give you an example, so that you're able to apply a Newton iteration, a Newton-like iteration, without ever computing the Hessian, which is out of the question for almost all machine learning applications. So we're going to have a Newton method that is Hessian-free, and that we're going to call the Newton conjugate gradient method, because just to call it the Hessian-free method is not a very good term. The steepest descent method is Hessian-free. And the Hessian-free aspect is important here, but a more important aspect are the properties of the conjugate gradient method. Okay, by applying an iterative method to solve the Newton equations, we're going to obtain algorithms that can truly be regarded to be somewhere in between first-order methods and second-order methods. And so the reason why I start these lectures with the Newton CG method is that one particular case of it is just steepest descent. And another particular case is the classical Newton method. And in between, we find tools that are going to be very useful in practice. Okay, so suppose that the problem is convex. Well, that's not the case of neural nets. But let's suppose that it's convex, because I want to understand things in that context. And then just say, oh, if the problem is not convex, never mind, just do whatever you were doing anyway, and take a few precautions. But this is really the way it's going to work. Newton's method makes a lot of sense when the problem is convex. We're going to understand it to death, and then say, never mind, just go ahead, charge ahead, and take a few precautions. Okay, I'm going to show in a few slides that if you solve the Newton equations by performing any number of conjugate gradient iterations, you will get a productive steps. And this is not true if I apply some other iterative methods. So if I apply Gauss-Seidel, or I apply GM-Res, or many of the other iterative methods, it is not true that if I apply, say, 5 iterations of such a method, I will get something useful, or 10, or 1. I may have to look at the residual or other functions in order to do that. But with the conjugate gradient method, I know that if I do 1 or 2 or 5 or 10 or any number of iterations, they are productive. And I want to explain, with pictures primarily, why that is true. Okay, so before we charge ahead, here are a few comments about this famous conjugate gradient method for solving linear systems of equations. If I want to solve the system AX equals B with A symmetric and positive definite, why symmetric? The Hessian matrices are always symmetric. So for optimization, we're always going to be dealing with symmetric matrices. So if I want to solve a linear system AX equals B with asymmetric and positive definite, I'm also looking at the problem of minimizing a quadratic form. So these two problems are equivalent. Solving a linear system of equations and solving a quadratic form built with A and B in that manner are equivalent because the gradient of this function is AX minus B. That gradient is equal to 0 when AX is equal to B. Right? So this is for the convex case. And now these two problems are equivalent. And what we're going to do is, when we look at the problem as a minimization problem, we're always going to be talking, of course, about the gradient of the function we want to minimize. When I look at the solution of a linear system of equations, then I'll be looking at the residual. So what is the residual in solving this system? Well, it turns out that if I define the residual as AX minus B, it coincides with the gradient of the objective function. So I have two parallel problems, a quadratic minimization problem, a linear system of equations, the gradient and the residual, and they're all parallel. So I can switch between one and the other. And the conjugate gradient method, I'm going to give you a picture that says where it came from. It's given by this iteration. I mean, the only important thing is it can be seen as a descent method for minimizing a quadratic function that at every step computes a search direction as a combination of the gradient and the previous direction. And the weighting is given by this particular formula. That weighting ensures that you have conjugacy, and that means termination. And then the iteration has the familiar form of, let's just move a certain distance along the direction that you found, and that distance happens to be the minimum of the quadratic function along the line that you're exploring. So one can easily derive the conjugate gradient method based on conjugacy considerations. So this is the iteration that solves linear system of equations in a very effective manner. Now, when we look at that iteration, we realize that we don't really need to know what the matrix A is. In this method, all what we need to know is what is the product of the matrix A times a vector P. If I can compute that product, then I don't need the matrix. And you're going to say, you're playing games here. How can you compute the product of a matrix times a vector without knowing the matrix? Well, in general, I can't. But if this function happens to be the Hessian, then I'm going to be able to do some tricks. And I'll show you an example here about how you do that. So in any case, we isolate this operation here. There it seems like there's another product, but one can reuse this product in order to use it there. So only this product is needed, and that allows us to do a Hessian-free algorithm. And the way the conjugate gradient method works, like any iterative method, you start by choosing an initial point x0. You don't know what it is. Then the very first direction, which is not specified here, is equal to minus the steepest descent direction. So the conjugate gradient method starts by taking the steepest descent direction on the quadratic form and then applies that iteration. And it will converge in at most n steps. Now, there's one particular case of interest. Suppose that you start the conjugate gradient method from the vector 0. If the initial point is 0, what is the initial residual? Well, the initial residual is minus b. So when I look at the search direction, it's minus b, minus r is equal to b. Okay, so if I started at 0, the steepest descent direction will move along the direction of the right-hand side vector b. And that's going to have an interpretation in terms of our outer optimization problem that I will give you in the next slide. So just to summarize here, we can start the conjugate gradient method with any vector. But if you started with the 0 vector, you will find some special properties. Okay, so I noted in the previous slide that if you start with the initial vector of 0, then the initial residual minus the initial gradient, the steepest descent direction, is equal to b. Now let's go back at what we were doing. We were actually interested in Newton's method. Well, here is a system of equations that you solve for Newton's method. If you write it in the form ax equals b, it turns out that b is equal to minus grad f. So minus r then is equal to, so r is equal to minus grad f. In other words, if I now go from the inside conjugate gradient iteration and interpret that in terms of my outer optimization problem f, the very first step that the conjugate gradient method computes is the steepest descent direction for the original problem. It's not just the steepest descent direction for the quadratic form associated with the linear system, it's also the steepest descent direction for the nonlinear optimization problem that we have there. And if my description is not so clear, then you can just check these slides and see if I got all the minuses right, which I did because I just checked them. All right, so this is then the official picture of the Newton method with a conjugate gradient inner iteration. You're at a point xk. Suppose that the objective function you want to minimize is quadratic. Why do I suppose that it's quadratic? So I can draw nice contour lines. But let's just imagine that's some optimization problem. So this is a machine learning problem. This is a nonlinear problem. It could be convex, not convex, but this is stylized in that way. I started with a point xk, and Newton's method tends to point, if the problem looks almost quadratic, to the minimum of that quadratic. So this was the perfect Newton step, goes almost to the minimum there. And what the conjugate gradient does is it gradually computes the Newton direction by iterating. And the very first iterate computed by conjugate gradients is the steepest descent direction for the optimization problem. So it really looks like that. That's my first estimate of the Newton step, and other estimates keep getting closer and closer to the Newton direction. So yeah, that's a picture worth remembering, and it's going to be backed up by observations that I have here. First of all, let's just give a blanket result that tells you how effective and how clean this method is. So a theorem. Consider a Newton method where you perform any number of conjugate gradient steps. Maybe 1, 5, 10, or some adaptive criterion. Any number is valid. Now suppose that f is strictly convex function. The function we want to minimize is strictly convex. And then you're going to say, who cares? My function is not strictly convex. Even the logistic function is not strictly convex. Fine, I'm going to give you a theorem because I'm going to do the usual thing of saying, here's a nice result, and then if you just do something, you can get good results too. I'll tell you what they are. So the idealized case is a convex function, strictly convex function, conjugate gradient method applied any number of steps to obtain an approximate Newton direction that I now wrote as this. There is a residual there. So I didn't solve the Newton equations exactly, and I'm not even going to get close to solving them exactly. After I get the search direction P, we do a backtracking line search of the type that Steve Wright was describing, a backtracking Armijo line search, which means try alpha equals 1. If it doesn't decrease the objective function, try 1/2 and 1/4 until you get a decrease of the true objective function. Okay, so a method of this kind, a Newton-like method of this kind, with any number of CG steps will give you a convergence to the solution of the problem. If the problem is not strictly convex and it's non-convex, maybe with lots of minimizers, the result is going to be that this method is guaranteed to converge to a stationary point of that problem. Now, a stationary point could be a maximizer, minimizer, or an inflection point. However, if you have an algorithm with a line search, every time decreases the objective function, it is very unlikely that this algorithm will land at a maximizer. So therefore, methods like this will either converge to minima or to saddle points. And they cannot avoid saddle points. It's in the nature of the algorithms. Any gradient type method cannot escape a saddle point. If I start at a point like this and the gradient is 0, the algorithm will not move. Okay, now, as I mentioned, the nice thing about this algorithm is if you do only one conjugate gradient iteration, you get the steepest descent method, and if you do n, then you get Newton's method. So I love this kind of algorithm because it gives you that flexibility. You can go from linear to subquadratic convergence, and it inherits some of the scale invariant properties of Newton's method that I will explain right now. So Steve Wright, I saw him talk about scale invariance, but let me just emphasize this again. Suppose that you want to solve an optimization problem whose contour lines are almost circles. So if the contours are almost circles, the steepest descent method works great. So are there cases where the steepest descent method is great? Sure. When the problem has a Hessian that is close to the identity matrix, if you start anywhere, the steepest descent direction points closely to the solution. Fine. Now, take the problem and change it into one with very elongated contours. Now there's a big difference between the steepest descent direction and the step to the minimizer. They can be almost perpendicular to each other, the more ill-conditioned I make the problem. So no longer is steepest descent a good method, but in either case, the Newton direction, if this problem is quadratic, it always goes to the minimizer in one step. And how do I go from this problem to that problem? I go from one well-conditioned quadratic to an ill-conditioned quadratic by an affine scale of variables. Just rescale the variables and you go from one to the other. Newton's method is going to be insensitive to that. It will always go to the minimum of that quadratic function regardless of the scaling that you did. That's the scale invariance that we aim to attain. For large-scale problems, I tell you, we will never be able to attain it, but this is what we would like to have. Quasi-Newton methods are sort of scale invariant. They're not quite. And the Newton CG method is going to be more scale invariant the more CG iterations you perform. Now, where's Eric? Is Eric G here? Okay. Now, you're going to stop me and ask questions or you're going to tell me it's going too slow. Come on, pick up the pace. Are you, Eric? Okay. So what are you saying? Pick up the pace. Okay. Pick up the pace. What do you do in the non-convex case? Well, a standard strategy for dealing with a non-convex case is this system is no longer symmetric and positive definite. Something you can do, add a multiple of the identity to the Hessian matrix to force the coefficient matrix to be positive definite. This is the Levenberg-Marquardt method. And now you solve this Newton-like system. It's no longer the exact Newton system. If you choose gamma large enough, then you no longer have a Newton-like method, but you have something that is based on a positive definite matrix. And here is a very simple linear algebra observation. If I have any matrix and I add a multiple of the identity matrix to it, the eigenvalues of the original matrix get shifted by gamma after I add that value to that. So if gamma is larger than the smallest eigenvalue of the matrix, then this matrix becomes positive definite. And so here is one very popular technique for applying Newton's method in the non-convex case. Add somehow, by black magic, add a multiple of the identity to the Hessian, make it positive definite, and everything looks as before. You have a positive definite iteration. It's not the true Hessian, but it's sort of Hessian, and so everything else should work. You can use the conjugate gradient method, and everything will work. But what's the problem with this approach? If you have a matrix that has negative eigenvalues, and I shift them so that all of them become positive, how far should I shift them? Should I shift them so that the most negative eigenvalue becomes 10 to the minus 6, or becomes 1, or 10? And that's where the problem is. And that's where the Levenberg-Marquardt idea since the 50s has been one of difficulty. I don't really know how much to shift. But this is still a method that is used a lot in practice. People will say, well, I adjust it for my problem, I make it positive definite, and things will work. A trust region method will automatically choose a value of gamma here. I will describe the trust region methods in a moment, but what is going to be very interesting is that sometimes the value that the trust region algorithm suggests is totally counterintuitive. You may have a problem where the matrix has a negative eigenvalue of order 1, and the trust region method suggests that you use a value of gamma of 100, something you would have never thought. So that conjugate gradient method will do that. So what other things that we could do? We could replace the Hessian matrix by the Gauss-Newton matrix if it's a least squares problem. The Gauss-Newton matrix is always going to be symmetric and positive semi-definite, maybe not positive definite, and we could use a multiple of the identity. And here's another thing that is done often in practice. You can stop the conjugate gradient method early, and what it will do is it will explore the positive definite part of the Hessian. I think I have a picture here. Suppose we have a non-convex problem and I want to apply the Newton CG method. Now I'm at the point in the talk where I said, what do we do when the ideal situations for Newton's method are no longer there? And the answer was just charge ahead and let's fix things a little bit. So you apply the conjugate gradient method to the system that may not be positive definite. And as soon as the conjugate gradient method finds that a product of this form is negative, and the conjugate gradient iteration, there is always a product of that form, and it always has to be positive if this matrix is positive definite, the conjugate gradient iteration will immediately flag you if it has seen a direction of negative curvature. Okay, and now let's go back and remember what we're doing. We really want to solve a nonlinear optimization problem, but we replaced it by solving this linear system of equations to compute Newton's method. This system is equivalent to minimizing a quadratic model. It's for that quadratic model that if I find negative curvature, I find that it's not convex, the conjugate gradient method will flag that for me. We can always stop the conjugate gradient iteration. So here's the conjugate gradient iteration, and at some point, the conjugate gradient method is trying to move along a direction that no longer has positive curvature, but negative curvature. So what you can do is, at that point, terminate the CG iteration. Either not take the negative curvature step or follow that to the boundary of the trust region. And these are techniques that are used a lot in practice. They work fairly well. I'm going to tell you, so I'll just put a couple of slides and then I'll start talking about how to apply this method in machine learning. So just to summarize everything that I've said, which is pretty much textbook material, the Newton CG method dates from the 1980s, developed for unconstrained optimization and systems of equations. There is actually something that could be called the Newton CG method earlier by Polyak in the 1960s for bound constrained optimization. The gradient projection method with CG, a very interesting paper, has sort of the essential idea of a Newton CG method. The fact that the conjugate gradient method can be used in a Hessian-free environment was identified early on, And this business of shifting the Hessian to make it positive definite that dates back to the 50s with Marquardt and so on was made more robust in the 1980s with trust region methods. And trust region methods became very, very popular in the 80s. And they're used extensively in many areas of optimization. So they give you a robust way of choosing that shifting parameter. Today, the Newton CG method is considered a premier technique for solving large problems. It's one of the best things you can do for deterministic optimization, together with nonlinear conjugate gradients or quasi-Newton methods. And it is used, Newton CG is used extensively in operations research and PDE optimization and so on. All the ideas I'm going to describe here that are going to be specialized for machine learning have been explored. For instance, in interior point methods, active set type sequential quadratic programming methods, augmented Lagrangian methods for general nonlinear programming. And they've been very successful there, and they're part of commercial software that scales up into the hundreds of thousands or millions of variables. But there are challenges in machine learning. We cannot just take everything that was developed for nonlinear programming and apply it here. And that's where the fun is going to start after all this background that I know was moving very slowly, but I was deliberately doing that. What about the application of Newton CG to stochastic problems, like in machine learning? So Martins, I can't remember what his name is, one of the students at Toronto proposed what he called the Hessian free Newton methods for training neural nets, and he got some very interesting results. And at the same time, we were developing a Newton CG method for logistic regression with a group at Google, and we got some very good results, and we started expanding them in different directions. So the first 5 points are the history of deterministic optimization, and then when we go into machine learning, all what we look is at the fact that the objective function is stochastic, and we're going to take advantage of that. So I'm now going to get into this guts of this Hessian free Newton method. Now, before I get into that, I guess since today is late in the day, so I thought maybe this is the day where I can make all these statements instead of putting lots of equations. Let me just make a bunch of statements so that at the break, a lot of you can come and attack me. And because, in fact, maybe some of you know that some of the statements I make here are not true. Maybe you've seen that this is not the case. But in any case, although I'm here making a big case for Newton-like methods, I have seen no argument to suggest that the Newton-like methods is better able at locating lower minima than first-order methods. I've never seen such an argument. But it is made in papers of machine learning. In any case, the argument is like this. A neural net is nonlinear, has minimizers. If you try to go with a steepest descent method and it's shallow, you may get a shallow minimizer. Whereas if you try to take a Newton step, you're going to get a better minimizer. Well, that may be true, but I've never seen any argument to support it. So in spite of that, I know there are groups that are obtaining good results with Hessian free Newton methods. And by the way, I should say that, I don't know if I've written it here, yeah, that this argument that you may get a better local minimizer is much more plausible when it's made in the context of stochastic gradient methods than when it's based on first versus second order information. So second order information, of course, is very good at turning corners, at getting you to the right place. But when at the beginning of the talk, I mentioned about controlled experiments. Can we do controlled experiments to try to shed some light into optimization methods? This is something that we could do, and we have done it to some extent. Well, what about if you take a Newton CG method, run it with one CG iteration, see what kind of local minimum you get, then do a more extensive conjugate gradient solve, see what kind of local minima you get, and so on, and see if really that's a tool for getting better local minimizers. And the few times we made experiments like this, we never saw that. On the other hand, if you switch from a deterministic method to a stochastic method, then things may change. So this discussion may be more interesting when there is some stochasticity at the optimization problem, as is the case for stochastic gradient method. The other thing that I should say is that I just glanced over trust region methods. I know they're not appealing for many people doing large-scale machine learning because there's somewhat of an overhead in using trust region methods, but they should definitely be tried. Because if there is a way to try to control where you want to go, trust region methods will do that for you automatically. And so I believe that Jan was telling me this morning about imposing a ball, doing a minimization in a stochastic gradient method, staying within a certain ball. And well, a trust region algorithm, that's the idea of the algorithm. Not perform the whole optimization within a ball, but perform a step within a radius that you control as you go along. So I don't know that people have tried trust region methods. They may be expensive, they suffer somewhat of scale invariance, but they should be tried in a controlled setting. Here's a little math to try to understand what Newton's method does, because there's also some misconceptions that I see here or there in papers. We don't really need to know much about Newton's method, but the inexact Newton method. What can we say about that? Okay, if you take the Hessian matrix, so let's suppose, again, for simplicity, that the Hessian matrix is symmetric and positive definite. Let's compute the eigenvalue decomposition of the Hessian matrix. Now, so therefore, lambda are the eigenvalues and V are the eigenvectors. So this whole big matrix can be written as the sum of eigenvalues plus VVI transpose are the eigenvectors. Now, the nice thing about the eigenvalue decomposition is that I can write the inverse matrix explicitly. So the inverse is given by 1 over lambda I times VI transpose. So the decomposition just differs in that the eigenvalues became the inverses of each other. Okay, so let's look now at the Newton step. The Newton direction is obtained by solving this linear system here. So let's bring the Hessian to the left-hand side, and that gives me the search direction Hessian inverse times the gradient. Well, when I write the eigenvalue decomposition of the Hessian inverse, I get that the Newton direction is equal to, let's multiply this decomposition times grad f. So I have grad f times that term times VI. And so what I see is that this is the exact Newton step, is now written, I've taken like an X-ray of the precise Newton step. It's the sum of terms along the eigenvalues, along the eigenvectors of the Hessian matrix. But they have different weights. So the Newton direction is a linear combination of the eigenvectors of the matrix, and that's not surprising. The eigenvectors of the Hessian span Rn, but the weights are given by the inverses of the eigenvalues of A. That means that the smallest value, the smallest eigenvalue will contribute the most, and the largest eigenvalue will contribute the least. To rephrase this, the Newton direction P is going to be biased towards the eigenvectors corresponding to the smallest eigenvalues. And you can see it here with this ellipse. The more elongated this ellipse, the more the Newton direction will turn towards the eigenvalues that are the smallest ones to obtain. So this is what it will do for you. And this is why the Newton step is very expensive to compute, because you need information about the smallest eigenvalues, which are the most difficult to obtain. But now, the Newton direction is very wise in that it knows how to turn. So when I see pictures in machine learning about people saying steepest descent is going along this shallow direction and Newton's method is turning, well, yeah, it is very good at finding a direction that is pointing towards the minimizer. But it's also very good at getting the length of the step correctly. And that's also very important. So for instance, in the stochastic gradient method, the gain is a very difficult parameter to choose. Whereas the step length parameter for Newton's method is very easy to choose. Normally it's 1, choose 1. because the scale is given to you by the eigenvectors of the problem. Okay, we want to design methods for machine learning that are now not as idealized as Newton's method, but have those two properties. First of all, they tend to turn towards the right direction, and they have the right length. The step length of 1 is going to be working most of the time. These are two rules that I'm going to impose, and the other rule, of course, is we have to have algorithms that scale up for machine learning applications, and that combine Newton's CG and all this Hessian information in the right direction. Okay, I don't know what this matrix said. I'm going to talk about these few things there tomorrow. Okay, right now I'll talk about the first concept that is applicable to machine learning, and that's Hessian subsampling. We've mentioned that you don't have to solve a Newton system exactly. In fact, you don't have to build the Hessian matrix very accurately. You can do a sampling of the Hessian, and that is going to give you very good results and the properties that I mentioned here. So now, here is the picture. So this line here represents the number of training points that you have. Let's suppose we were doing supervised machine learning, and that I have 168,000 training points. If I use only one training point at a time, I'll get a stochastic method. If I choose them all, I have a purely batch method. What we're going to do is we're going to look at the Newton CG method that uses a substantial amount of information to compute the function and the gradient. How much is that? Well, you can do a mini batch. Maybe it could be 10,000 elements or so on. But X is the sample to compute the function and the gradient. That's going to be relatively large. But in order to compute the Hessian, I'm going to use much less information, maybe like only 1% of the training points that are used for the function and gradient, we're going to use them for the Hessian. And this is going to work. What is surprising is that this is going to make a sensible algorithm because of one key observation that is written in optimization books, but that it probably should be written in gold, because it's something that has to do with potential functions and the differences between optimization and nonlinear equations. The observation is that if you have an optimization iteration of this form, if you start introducing errors in the gradient, they're important. However, if you start making perturbations in the Hessian, they may not be important. An optimization iteration of this form is very tolerant to what you do to the Hessian. And why do I say this? Well, for example, if instead of putting the true Hessian here, I put the identity matrix, that is not a garbage method. That's steepest descent. At least it goes downhill. If I put any positive definite matrix, I still have a descent direction. If I put a low rank correction of the identity, which is what quasi-Newton methods do, I get productive directions. There's a lot of freedom in choosing that matrix. And we're going to absorb that freedom in machine learning applications by computing this Hessian using only a few sample points. And that's going to be called Hessian subsampling. And that appears in the paper of Martins too, and in our paper, but we exploited this concept extensively. So here it is precisely. Suppose that the objective function is the sum of terms, loss terms, 1 for each training point. The gradient, this is a mini batch, is going to be based on a sample of size x. So I'm going to put this on the right-hand side of the Newton system. And how to define this, I'm going to discuss that right now. But for the Hessian, we're going to choose a much smaller sample size. Now, the objective function, the important thing is that if you have optimization problems whose objective function is the sum over the whole set of training points, then you can reduce the summation by picking at random some points. So in the same sense that this mini batch gradient is obtained by choosing at random some training points, maybe 1,000 of them, I'm going to, when I look at the Hessian, if a function is the sum, the Hessian is also the sum. So when I look at the Hessian of this function is the sum of all those training points. let us choose only much fewer of those training points. 1% of whatever I use for the objective function, I put it in there, and now I have a Newton iteration where this Hessian, there's a subscript S there, and that gradient used different number of training points. This is going to make things feasible. Then we're going to apply the conjugate gradient method to that, and we're going to coordinate the sizes used for the Hessian and for the gradient so that the number of CG steps is not very expensive. So for example, if the sample used for the Hessian is only 5% of that used for the gradient, and I use 10 conjugate gradient steps, then one total conjugate gradient cycle, one whole Newton step, is going to cost me less than one function evaluation. What I'm saying here is that I am describing a Newton CG method whose cost is very similar to a steepest descent method, but whose properties are going to be very different. Now the cost is going to be twice as much, approximately twice as much as that of a gradient method, but this method is going to be able to turn, it has curvature information, and it's going to have the right length. So for example, on logistic regression problems, typically what we see is that in the first or second iterations, we need to do a line search to adjust the step length. After that, the unit step length will work. And any optimization algorithm for which the unit step length works has some wisdom. It's too much of a fluke if the unit step length works. And by the way, for the nonlinear conjugate gradient method, the unit step length never works. For the nonlinear conjugate gradient method, you always have to worry how to do a line search. It doesn't have enough curvature information. Newton CG does it, quasi-Newton methods have it, but I like this framework over limited memory, BFGS, or so on, in terms of the flexibility that it gives us for solving the problems. Okay, now I've almost used up the time. Tomorrow I'll tell you a little bit about how is it possible to compute Hessian vector products without knowing the Hessians. It's going to be magic. It's actually going to be trivial once you see it. But I just want to give you a preview of what's going to be in tomorrow's lecture. I'm going to describe inverse covariance matrix selection problem. And I'm going to produce some numerical results that were really surprising for me. So some of the results are going to be based on a Newton CG method that we're going to build. We have the foundations now. We're going to be able to apply it to matrix problems. And when compared to the alternating direction method of multipliers that Steve Wright discussed extensively here, we're going to observe, these are CPU times on a couple of inverse covariance matrix problems, and the alternating method of multipliers and methods of that kind were the only things that people were using up until recently for solving inverse covariance matrix problems. They were considered to be very difficult because their matrices are Kronecker products, and the difference in CPU times, as you can see here, is extremely large. That's why I invested so much time in talking about Newton CG. I'm going to use that a lot. Finally, as a preview of what we're going to talk about tomorrow, if you look back at machine learning problems, they're really statistical learning problems. We would ideally like to minimize expected risk functions that are integrals of this form in the space of input-output pairs and probability distributions. And in practice, we use empirical risk or empirical expectations. And in practice, we use approximate minimizations. So at the very beginning, I was talking about balancing those objectives and some statements that are being done by Bottou and Bousquet in their paper. Well, this is the last slide of today. What it says is that if we look in its totality, the machine learning problem, there are really three approximations that we make. One is we choose a set of prediction functions that may not be the right one. So we may use prediction functions for speech, and we're going to hit a wall because we don't have the right prediction function. The second is we don't really know what the probability distributions are, so we work with empirical expectations that are summations, and they contain errors and they contain redundancies, or we choose few of those. So there is an approximation error, which has to do with approximation theory. Then there is the estimation error, and then there's going to be the optimization error. And in principle, you would like to bring down these three, but what we want to do in practice is to bring them down in a gradual way. And my part is just the optimization part. The optimization part has to synchronize with that, has to be tailored to that. Okay, so thank you for your attention.